Next slide. So this is the same thing with what we are doing. So this is C, observe over here, this is the final part of it. So when we are looking at the scenario where the region A and the region B has been considered to be two specific segments. Right? Now let's see, we get into a little bit more detail of it. See if you can understand this very clearly, understand this, because this is a very interesting set of questions, but I am unfortunately the projection is somehow showing a little bit problematic over here. Let me just, because I want to, let me do one thing, 1 minute. Because I want to show you the whole image, otherwise you won't be able to understand. Let's see if it works now. Yeah. See this image particularly, not the image but the problem particularly. Okay. Now if you observe carefully what is actually happening over here, we have an image which is a gray image. Right? And if you observe carefully in the gray image also, intentionally there are portions which is deep gray, which are light gray. Somewhere the illumination is pretty high, somewhere it is very dark. So if you observe this part, little bit grayish but little less in the intensity. It goes on to this part where there is a lot of darkness. In specifically, we have a dot over here which indicates a white dot. Okay. Then again you have a line which comes somewhere over here, which is fairly somewhere between the dark and the white. And then again there is a dark, and finally there is again some white. Whatever, right? This thing. So this is a portion of the image. Suppose this is a portion of the image, and we have to find out, or we have to do it, the edge detection on top of this. Now here if you observe, the pixel values are not given to you. There is no specific pixel. So you, from the intuitive understanding, you can say that by looking at the image that these are the possible ways in the edges can be considered. But if you observe over here, there is a profile which is given over here in the first page. This one. And this is called as intensity versus the pixel value. So if you observe, the intensity has been provided over here, and if you go closely, these values, like each of these values are indicative to the image strip over here. Can anyone observe this? Everyone can see it. Image strip is an array of element where we are storing the particular value which is given in this particular profile. This profile is what indicating that suppose it has a straight line. It goes something like this. So it is like started from this point. Perhaps it has started from this point and it is going through this white dot and further like this. So it's a row wise. It's going like scanning like this. Okay, it's row wise. Now suppose it is at this point. So we are getting some values 5, 5. So you can see 5, 5. So the points are 5, 5. Similarly 4 and all, how it is going on. So like that 4, 3, 2, 1. It's going like this. Now over here somehow we are assuming that near to this point of white dot, it is more towards the dark region. So you can observe that it is more towards the 0 region. Okay? Now if it is 0, after a certain period you can see, since the white dot is pressed over here, there is a huge spike that goes up. That's a huge spike that goes up. And finally, since it is only a small region, after that suddenly it drops down. And likewise the rest of the profile has been maintained. So this is what we call as the image profile without the exact value of the grid structure that we are looking at. Row wise we are like as if scanning. So in the process we are intentionally scanning in this particular region where the white spot is indicating a sharp change. Now in those cases you can see this is a ramp edge detection, we call it that. We'll see that in the next slide, but don't look at it that way. Going down steady towards the dark, suddenly going up, which is high, which is a white color, again coming down because the intensity is staying for only small segment, and finally it goes to up here. Again if you observe, when it reaches somewhere over this side where I have made a mark, again some kind of a up value is observed. And after a period, it again dies down because this is dark. And finally, when it reaches over here to this segment, the graph goes up again. Okay? So this is basically a profile, we call it, for an image in order to do an image processing application. But now the question is, where come the edge detection comes in? So in order to find out the edge detection, what we have to do is, we have to first do something called as the first derivative of the image strip. And what is that? What we are trying to do is, we are just trying to make a difference. Please understand and remember this carefully because the statement might be missing over here. The difference between the two set of image strips, okay, and whatever be the difference, that we are initiating over here. So basically what we are trying to do, 5 minus 5 is 0. 0 is supposed to be here. The 0 is missing. There is supposed to be a 0 over here. There is a 0. 4 minus 5 is minus 1. 3 minus 4. 3 minus 4 is minus 1. 2 minus 3 is minus 1. 1 minus 2 is minus 1. 0 minus 1 is minus 1. 0 minus 0 is 0, so on and so forth. Until you get a point where you are observing that there is a high value of 6. Because remember, what our objective is to find the strong change in the signal intensity. We don't have any threshold, we don't have any seed point, remember. So we are trying to identify the strong change. So using the first derivative, what we are observing, that we are getting some minor values over here. We are getting definitely one high value, which is 6 over here. We are also getting some value minus 6 also over here. Okay? And finally we are reaching that 7 also. See over here, last 7 as well. So we get some kind of a data smoothing or a data pre-processing from where we get an idea about the image intensity. But that is not the all. We are still not sure about where exactly the changes have primarily happened. We more or less tentatively we can understand. In order to refine that search, we have to do the second derivative, which is nothing but taking the difference between the values what exists in the first derivative. So minus 1 minus of minus 1, that is plus 1. So it should be a 0 over here. There is a missing 0. Okay. Then we have minus 1 and minus 1 we have over here as 0. You can see. And accordingly we go on. Interestingly, what you can observe that over here 6, then we have a minus 12 and we have a plus 6. Can you see this carefully? So at this point, with this second derivative, after we have done the second derivative, we are observing that most of the points are coming as 0 or in terms of 1 or negative value we cannot do it. So it will be ignored after all anyway. So the important part is that we are observing a significant change over here where the data is varying between 6, it goes to minus 12 and again it goes back to 6. So there is a change, a significant change that we are observing. So what happens is that in an image segmentation, if we are doing an edge detection, an algorithm will run through the image. It will go on scanning each and every time, and this kind of an first order derivative and second order derivative will be taking place with respect to x-axis. And we'll calculate the differences, and whenever we'll find the refined image strip with a portion where there is a significant change, we'll consider that there is some kind of an edge that exists over that particular portion. So in your questions, in your exam, maybe you will be given such an image or you may be given such a profile. You have to find out what is your first derivative, what can be your second derivative. And you have to identify or conclude on the remark saying that where exactly you are finding the changes, and accordingly you can draw the profile of it. Even sometimes the profile can also be given and nothing is provided. Maybe you are asked to find out what is your image strip, what should be your first order derivative or the first derivative, what will be your second derivative. Accordingly conclude your answer. Okay? So remember one thing, for the edge detection we don't require any thresholding, we don't require any seed point. but we will only have to find, or rather we have to refine our search in order to get the strongest change in the image pixel value or the intensity value for the graph. Okay? This is one of the important aspects. Now, if you observe over here, there are certain portions which has a ramp and some portions which has spike. Some portions we have a steady changes. So that based on that, we can also have some classification of edge detection. This is like more towards the detail of edge detection, which is not required as such. But as in this example, we are coming up with all this. So maybe just one point we can say. So step edge is the image intensity abruptly changes from one value on one side of the discontinuity to a different value in the opposite side. So basically what we have it somewhere over here. Okay, it was somewhere around 0 and it's going to 7. So it's a steady jump that happened. Okay, so that is what we are talking about, the step edge. Second one is rampage, where there is a gradual change. If you observe, this is a negative ramp that we are looking at. Similarly, there can be a positive ramp maybe over here, you can say the small segments over here. So that's a ramp. When there is a steady change. A ramp, a step edge where the intensity change is not instantaneous but occurs over a finite distance. Quite obvious and understandable, I guess. Ridge edge and the roof edge, these are always mostly available over here. As you can see in this particular example, when we have only a white spot. So there is a huge spike suddenly out of nowhere. So that actually comes under this ridge and the roof edge. So the intensity change is not instantaneous but occurs over a finite distance, is roof edge. But ridge edge is basically what we have observed. If the image intensity abruptly changes value, but then returns to the starting value within a very short duration, like an impulse response. It goes up, goes down. That's it. Okay, so those are spike, the ridge edge we call it. Like in terms of the edge detection, we call it the ridge edge. So if you observe, these are the kind of, if you say it with respect to image, you can see over here, this is another example. So this is black. Most probably this is white. That's why it is not coming over here. So this part is white. So black to white, there is a steady change. So step edge will be like this. We have this is a gradual change that is happening. So definitely that will be a ramp. And the last one that you can see in the middle, there is a huge white space or a spark over here. So basically there is a high intensity which is provided. Right? So this is all about the edge detection techniques, and thus the segmentation is complete. So this is where we stand at this point. Image captured by the CCD sensor. If you remember before CAT1, we have done the CMOS technique and the CCD sensors. So that is part of it. After the captured image, digital image is stored and data is reduced. This is where the masking techniques will come into handy, and we are reducing the size of the images using the average, median average methods or the neighborhood averaging methods. Then we have to have the image segmentation. This is where the thresholding, the region splitting, merging, growing technique and edge detection is actually taking place. So now we are done with the last two parts, which is the feature extraction and the object recognition. So in case of feature extraction, basically what does that mean? That if you are given an image, okay, after you have done all this segmentation, you have bifurcated the foreground to the background. Now we need to extract out some information out of those images. And how you are going to do it, you need some parameters to do it, which is, I guess, fairly obvious for all reasons. You know that for some of the experiments, when you conduct the experiment, you will try to draw a plot of it. Like you want to have a profile. In that profile, you need something in the X, something in the Y axis. So you will vary some parameter in the X, and you will get some responses, and that you will plot in the Y axis, right? Same way, for the image also, there are certain parameters. So few of the parameters is what we are going to discuss in that a specific question we are going to discuss. The first of the parameters, please make a note of this. The first of the parameters of it is called as the center of gravity or the centroid in general, and is given by CGX. If you observe over here, CGX is given by 1 by n summation of x. It will be very clear after I take the example. For the time being, just note down the formulas. So it is basically simply the weighted average of all the pixels constituting the shape. So within a image, a portion of this is we are doing after the segmentation is over. So possibly the foreground and the background is managed. We are not bothered with the background. We are only focused on the foreground where the object is present. So Most probably you imagine a scenario where you are focusing only on the image. So that's basically what the shape we are looking at. Okay, out of a complete image, only the portion of relevance is what we are focusing on. The rest of the things is not our concern. In that, the centroid is one of the parameter which sometimes we will find out from an image from the quantitative analysis, and that is one is called a CG. So you can see CGX, it means this will be the CG, center of gravity, or we call it the centroid, will be a single point within that preferred portion. Okay. In that, the x-axis is given by the CGX and CGY indicates the y-axis, the y coordinate, not the axis, coordinate. So this is my x coordinate and this is my y coordinate of the point which will be considered to be a centroid. In that, what is the process of computing it? I'll let you know. In what you are looking at over here is the actual pixel of our interest. Maybe there are 1,000 or other pixels, but those are background. Only the portion of our relevance, the pixel which comes under that is considered to be the n. Okay? So that will, like averaging, we are all throughout, we are averaging it. So that's why 1 by n summation of all the pixel values or the intensities across x or across y. We'll see that with an example to make it more clear. The next parameter that comes in is called as thinness of the image. Alright, these are all again, as I said, these are all attribute to find out that suppose I want for my robot to have a particular value of thinness of the image to recognize. So we'll fit that value. Now suppose you calculate, your algorithm calculates the thinness to be less than that, then definitely you require more refinement of the image in order to perform. Right? So that is what the thinness is all about. So thinness is given by, please make a note, perimeter square to divided by the area. Perimeter square is here the whole area of the image to that of, the perimeter is the only the relevance portion of the image that you are looking at. Perimeter is the same rule, like the same meaning of the perimeter, like the edges if you consider, add up. So that square divided by the total area of concern. We'll see that again, we'll calculate that with a numerical. So this is thinness. Next is the moments. The moments we usually don't calculate as much in our examples, but even given a region R and coordinates x comma y in or on the boundary of the region, the pqth order moment of the image is given by this formula. So around the image, about the edges of the image, so the relevance portion and the non-relevance portion. In that portion, whatever be the value of x and y of the pixel, that will be considered and multiplied and taken average of it. Okay, not the average, but summation, some average. Alright, so this is the moments, but moments usually we don't take into account for our calculation purpose in most of the time. Now let's take the example. Please see this example very carefully. This is the only example available as such as of now, but similar kind of questions will come in your exam as well, or for your understanding. Okay, so I'll go slowly so that we can understand this segment. So if you observe this diagram, the portion that you are looking at as 1, all these ones that you are looking at is indicating the relevance image. This is the relevant portion. Okay? The rest of the portion that you are looking at, the white part, this is not relevant for us. So suppose this is the portion, this is the image as we have received after the segmentation is over. Okay, so after the segmentation is over, we are getting this particular structure. Now the question is, how many pixels do we have? We'll just calculate the number of pixels which are present over here. Number of ones. We don't need to worry much about what is there otherwise. We'll just calculate the number of ones. So if you observe 1, 2, 3, 4, 5, 6, 7, 8, 9 and 24 like that. So this actually gives you the value of n. So we are given any image of this nature, we are just going to focus on the relevant portion, and given that relevant portion, we'll just calculate the portions of pixel which consist of ones. Okay? Now, that's one thing done. Now, if you observe the aspect ratio calculation, aspect ratio will be nothing but length by that of the width. Now length and width you can calculate quite easily from the system. If you observe that length starts from here to here. Okay, so take the value and the width will be of this nature. Alright, so we can take 9 to that of the 4. The 4 is our width. Length is actually my n. Okay, so this is my length and this is my width. So we take an aspect ratio of 9/4. This is simple. This is not that difficult. This part is relatively simple. The doubt comes in when we try to calculate what is the centroid of it. So let's see whether we have that centroid. So now we calculate the centroid. We can see this diagram already the centroid has been mentioned over here. But for the time being, let us assume that we don't know where the centroid lies and we need to find out a way in which the centroid can be calculated. Okay? So let's see one by one how we are going to do it. Remember, the centroid is a portion where we are averaging with respect to certain parameters like x direction or y direction. So the rule is very simple. Follow this very carefully. First, what we are going to do is we are going to make some kind of a approximately grid of this nature. Okay, so we are not doing it actually, but this is like virtually we are doing some kind of a grid of this nature. This is the first step. Now, very interestingly, something will happen. If you observe that the image has a value or the graph over here has a value 0 over here and some x-axis and y-axis. What we have is, as I said again, we are going to only focus on the relevant portion. So my relevant portion is this t part. This t. So what we are going to do, we are going to shift this 0 to somewhere over here. Okay. And we'll go on giving the respective coordinates to each and every point. Can you follow this carefully how we are doing it? This is 0, 0. What will be this point? 0. This point will be 1, 0 because we are going towards the x-axis. 1, 0, 2, 0, 3, 0. This would have been a 4, 0, but we don't have anything over there, so we don't need to worry. We go at this particular point, 4, 1, because this is 4 and this part is we are moving towards the y direction. So that's why you can see this is y prime and this is x prime. Is it clear to all? We are making an adjustment so that we are only focusing on the area of our reference, not the whole. So we are keeping this as 0, 0 and based on that we are putting a coordinate to each of this small one box or the segments. So accordingly on the y-axis also we have to do. And if you observe in y-axis very interestingly what is happening that for a particular case the 0, you can see the x is not varying but the y is only varying. So that will play a major role over here as well. So now accordingly all the points will also have, but due to lack of space I am not able to do it. So each of these points will also have some coordinate. Can anyone tell me what will be the coordinate here at this particular point? It could be 2, 2. Correct. Like that for all the points are there. Okay, but for our reference we are not looking at it. Now after this is done, we have to calculate the centroid. So first what we have to do is, we have to take the middle point of all these individual boxes or the pixels. Just the middle point in the sense, we have to find the coordinates of each of these middle points. These green dots that you are looking at, they are indicating approximately the middle portion of each of the boxes. And we will assign some coordinates to them as well. So we can go on doing it for all the other greens. So you can see over here, what will be this point? This will be x-axis 0.5, y-axis 0.5. So this is a point which is 0.5. So 0.5, 0. This point over here, we go 1, 2, 3. So it is like around this part we have reached. So over here it is 2.5 and this point is, from this point is 0.5 because it is half of this. Guys, please understand this carefully because this is an important part of it. For all the points, you have to identify the middle point of each of the pixel. As we have framed our reference with respect to x prime and y prime axis, Now each of these middle points will also be given a specific coordinate, and that is given by this purple colored indicators. Is it fine? For all the pixels, all these green points, there will be some kind of a points. Now the question is that after we have done, we have to estimate the CGX. Okay? How we are doing it? CGX. Now CGX, if you remember the formula, it was 1 by n summation of x. So what we have to do is, we have to go on checking pixels, the green ones, for a fixed value of x, how many pixels we can gather together. Which means, if you check this point, the x value is 0.5. Okay? This point, the x value is still 0.5. This point, the x value is 0.5. This value is also 0.5. So all these points, if you take 1, 2, 3, 4, all these 4 points, we have x which is 0.5 constant throughout. 4 times 0.5. Is it understandable? We are going on checking for a constant x. For that particular constant x, how many pixels we can put together. So here we start off. So the first one has 0.5 as the x. And we can observe the one that is on top of it, that also will have 0.5. What will be the axis of, what will be the coordinate over here? 0.5 comma 1.5. 0.5 comma 2.5. 0.5 comma 3.5. So the y-axis is varying, x is constant. So 4 times 0.5 has repeated itself. It will come. It will come. That part I'm not doing. I'll do that. I'll show you next step. I'm just calculating the x part. Next part comes in with the next pixel. Over here, this point, we have 1.5. And if you observe carefully, all these are having 1.5 as constant. So 1.5 4 times we are repeating. Okay? 4 times, again 2.5, 2.5, 2.5, 2.5, 2.5. 4 times it repeats. We are keeping the x constant and we are going on finding how many pixels we can put together to find the centroid or the coordinate of the x point for the particular centroid of the image. Why this 2? If you check here, we reach over here. What is this value? What is the coordinate over here? 3.5. 3.5x, like for the x part, it is 3.5 here. 3.5 and 3.5. So 2 points are there which has 3.5. 2 points are there which has 4.5. So on and so forth. Up to this point you can see 17 by 2. The last point, if you observe over here, what is the value over here? The last point? It is 8.5 comma 1.5. Very good. What is this point? 8.5 comma. So basically 8.5 is the last recognized value of x. So you can see 17 by 2. You can take it as 8.5 also. Don't worry about it. But usually since this is much easier for calculation, that's why we are doing it in a fractional way. You can take it as 0.5 also, and in calculator I don't think it is required at all. It is half, 3 by 2, 5 by 2. But just to make you understand, there's a pattern to it. That's why I kept it this way. And finally, if you observe, after calculating everything and dividing this by 24 total pixel, if you go by this will be divided by 1 by 24, because 24 is the number of pixels that we have considered over here. The final answer that we are getting is 3.75. So that means 3.75 is the x coordinate of the centroid for the image in hand. Is it fine? Or how we are calculating it? So the first thing is, we have to make some kind of a grid element. From the grid, we have to first of all shift the base axis to that particular segment. And accordingly, we have to coordinate, or we have to make sure that the right coordinates have been placed accordingly. Next step is we have to find out, always remember that we have to take the assumption that the pixel's middle value of each and every box should be considered. The value we cannot consider anyway because this is indicating value is 1. We are not talking about the value, we are just considering the coordinate of that particular point. So in that also the assumption is we'll take the x constant and we will check how many such boxes we can put together. And similarly for the y also, we'll keep y as constant and we'll go on taking the y one after the another. Can anyone tell me for the y calculation, first element, just like here we had 4 of half. What will be the first entry for y? If you observe over here, we start off here again. So here the y value is 0.5. This is also 0.5. This is also 0.5. So basically 3 times. So ideally the first term should be 3 times half. So now let's see with the calculation itself. So this is the basic calculation that you're talking about. And as he was rightly pointing out, so 1 by n, don't forget that. So we have a 1 by n. In this n, we have calculated for this example as 24. So overall, we are calculating that as 15 by 4 unit. If this you take it, the value will come as 3.75 approximately. But that is only for x. Similarly, for the y, we have to calculate, as you can see, the first term 3 times half. That's what we have done. And again, the same way 24 comes over here and we get the value as 2. So basically, my centroid value is 3.752. Okay? So that's a property of the image, a feature of the image that we are capturing after the segmentation is over to find out whether the centroid is matching to our requirement. Okay? This is fine for all. So we have to find out the process in which we have to calculate the aspect ratio. We have found out the way in which we calculate the length of an image or the number of pixel in an image, which is nothing but the calculating of all the ones which is present. And very importantly, we have calculated the centroid as well. Last but not the least, let us calculate the compactness of it, which is given by the perimeter square to that of the area. This also is a simple process of calculating the perimeter, as you all know. So I'm not discussing that. Assume it to be a rectangular box. Accordingly, we get the area and the perimeter also you can find out from the same. Substitute and you get the value of 28.17 as the compactness. Okay? So these are all some of the feature extraction like parameters. There are many others in fact. There are many other parameters also, but they are not relevant and we don't need that much of detailing as such for our consideration because this is not an image processing subject topic itself. But as we have discussed so far, we have captured the image, we have segmented the image. We now in a position to understand what are the features we can extract out of the image. So the last but not the least, the segment that comes in that after getting all this information, what we have to left with is to detect the object. So that's what comes under the object recognition. So based on these features that we have extracted, whatever the information we have extracted, we will try to, the robot or the sensor, like the vision sensor itself, will try to visualize that what exactly is the type of image that we are looking at. So if you observe over here, template matching technique, this is one of the very oldest and one of the commonest of techniques that's being used. So in case of template matching technique is that we have some predefined nature of image classification. Like for example, the training model indicates that we have to have a cubic structure. Now cube will always have each and every side equal. So that is one of the feature. So suppose out of the feature extracted, we find out the information that all the sides are of equal. So then we will decide that whether it is matching to the template which was provided to us. If provided and if it matches, then we will say that yes, the image is correct. So you can see over here, known object category. Sufficient number of features should be known and trained to the robot. And finally, if matching happens, then some statistical change indicates the original object. So there must be multiple features of the object that we are looking at should be fed and trained to the robot based on the template. But the problem with this is that if suppose some alien object comes in and you have to do it, you have to retrain the system once again in order to make that thing happen. So that in fact gives you another one which is called structural technique in fact. This is also like pretty old, to be honest. But here also recognizing an object based on the relationship between the features. This is something different. Like for example, suppose you get a rectangular block and you get a cuboidal or a square block or a cuboidal block. Now, based on that, if you check the relationship between the length and the width, okay, you will try to have a feature which will indicate that whether it is a rectangular block or a cuboidal block. So that is basically the relationship between the features. So syntactic method of recognition, we don't need the feature like the training model. We don't require that much. It will just compare amongst the shapes and based on that and the relationship between the features, and it will come up with the result. For example, 4 perpendicular lines can make a rectangle or a square, but more details will reveal it is all what kind of shape we are looking at. Okay, so that is basically how we, after we are getting the information out of it, out of the images and the feature we are getting out of it, we have to make sure that we identify the object correctly. So in this segment of our vision sensor, I think this is where we end our discussion. What we have discussed is from the point of capturing the image using the camera module, the CMOS module, then after capturing the image, how the basic steps of image processing will finally lead to the recognition of the image or the object, not the recognition of the image, but recognition of the object compared to foreground to background. And what are the different conventional technique like edge detection, like the segmentation, like the feature extraction. Now there might be n possible algorithms to it. That is different. But all the cases, the image processing will have all the other steps. And based on those steps, we will finally recognize the image or the object and we will conclude the discussion. So that's all for this segment. So tomorrow onwards, when we come back, we'll start with module 4. As I said, unfortunately, we have a class at 8, but try to come by 8 itself, or at least for tomorrow's class, since we are starting off with the module 4. And as I said already, module 4, please be attentive and don't make absent as much as possible, because you won't be able to follow up, catch up, unlike to these topics. All right. Thank you.